Here we have an exercise about the contours involved in the derivation of the Laurent series. And the question is, can you change these contours around? Because if you recall, what are these contours? So for example, we had this rather funny looking contour, which basically looks like this. So two circles with a cut inside. And then the question is, can you change these contours? Can you, for example, shrink the radius of this inner circle and then have something like this over here? So how does that affect the results? The answer is that doesn't affect the results, because if you just follow the calculation, this radius of this contour doesn't really come into play. But try and convince yourself about the fundamental reason why this is the case. This goes back to a previous exercise where we said if you have a holomorphic function and you want to calculate a line integral, so you want to go from here to here, and basically it doesn't really matter whether you reach your point this way or whether you go that way, as long as you are in a region where the function is holomorphic. So have a look at that other video. It basically boils down to just changing the orientation of one of these contours here, of one of these lines here, such that you form a closed contour on which you can apply Cauchy's theorem. So more details in that video. We can also apply the same thing here. If we have now an integral from a to b, doesn't really matter whether we follow the black path and go like this from a to b, or whether we take the red path, first a little line segment, and then move around a smaller circle, and then back to b. So that doesn't really matter. The only thing that matters is the beginning point and the end point. As long as we are in a region where the function is still holomorphic. So this means that we should, of course, avoid entering that circle around the origin here where our function is not holomorphic. But as long as we stay out of this region here, everything is fine. That also means that we don't really need to have a circle. We can also, for example, do something funny and have something like this, right? So it doesn't really need to be a circle. We can also change it like this to be a little bit bigger. But one thing we cannot do is, so say that we want to calculate, for example, the Laurent series at a certain point z. One thing that we cannot do is change our contour to, for example, go like this. Pause the video and try to think about what's problematic of having this particular contour. The issue here is that if you look very carefully at the integrals of the contours that we evaluate here, they come from a series expansion, and that series expansion only converges if our z, we called it, I think, z prime, if our z prime that was running on our contour was in magnitude smaller than z. Otherwise, the series expansion did not converge. So if we change our contour to move here to a region where all of a sudden we now are bigger in magnitude than z, then that series expansion will no longer converge. But as long as you stay within this radius c here, and as long as you keep out of regions which are non-holomorphic, then you can change the form and the shape of your contours to your heart's delight, and nothing will change in the coefficients of the Laurent series.